Light, one of the cornerstones of the universe that keeps us from being plunged into darkness. We are so used to its existence that we rarely give it much thought. But what exactly is light?
You may remember that light is a wave, with different wavelengths being different colors. For centuries, scientists knew that light exhibited properties of waves like reflection and refraction. But in the early 20th century, this belief encountered problems. By shining light at metals, electrons inside the atoms were energized to the point of escape. However, the frequency of the light had to be above a certain minimum value. Otherwise, no electrons were dislodged, even if a massive amount of light delivering a huge amount of energy was shone. The wave model of light couldn't solve this problem, as it only associated energy with the total amount of light hitting a material. It couldn't explain why the frequency of light matters, since any frequency should be able to free electrons as long as enough is sent. The solution emerged in 1905 when Albert Einstein theorized that while light can act like a wave, it also acts like streams of indivisible particles known as photons that carry fixed amounts of energy that depend on the frequency of the light. Mathematically, the energy of a photon is equal to the frequency of the light times a number known as Planck's constant. Later discoveries by Niels Bohr showed that for electrons in different regions of an atom to be dislodged, specific minimum amounts of energy, known as the electron's ionization energies, must be delivered by individual photons. It's like when people look for a primary job. Every person has a unique minimum salary that they can accept and will only take one offer at a time. For electrons, energy rather than money is accepted from photons rather than companies. If the offer is too low, no individual photon can move an electron, and increasing the intensity of the light by sending more photons will only result in them all being rejected, as their energies can't be combined. Thus, the least amount of energy a photon should carry equals the minimum ionization energy of the electrons in the material, and the frequency associated with this energy is the aforementioned baseline for dislodging electrons. If the frequency were lower, no single photon would have enough energy to ionize an electron, resulting in none being ejected, regardless of the total number of photons and the total amount of energy delivered. This phenomenon, known as the photoelectric effect, solidified the idea that light can act like a particle while also being a wave.
The discovery of the wave-particle duality of light revolutionized physics. It set the stage for later discoveries like quantum mechanics, which in turn allowed for the development of technologies like the internet and the device you're using to watch this video right now. In short, similar to how light helps one find a path in the dark, our understanding of light's true nature has set us on the path to a brighter future.